Hello everyone, welcome to my YouTube channel. This is Karthik from Karthik's Tech Time. Recently I built a 10-liter agriculture sprayer drone. The airframe I'm using for this drone is a flagship model and one of the most popular airframe manufactured by EFT. I have integrated Hobbywing X6 Plus motors along with 24-inch propeller, all powered by lithium-ion battery pack. I have also integrated CUAV X7 Plus flight controller paired with C-Compass and Neo 3 GPS module. C-Compass is a high-precision digital compass module designed for getting more accurate heading data, which is essential for stable and reliable drone navigation. One of the most challenging tasks when using Pixhawk-based flight controller is tuning. In this video, I will guide you through the step-by-step procedure to achieve better tuning. When using a drone for any application, it is essential to ensure that it flies correctly. In the case of agriculture sprayer drone, proper tuning is important. Without proper tuning, the drone could become unstable, resulting in uneven spraying or even potential crashes. So, accurate PID tuning is essential for precise control of drone's movement. Well-tuned drones are more efficient in terms of power consumption. Tuning minimizes unnecessary movement and oscillation, which can drain the battery faster. So efficient tuning can help to extend the drone operational time, and it allows to spray more area per charge. I'm going to fly this drone in stabilized flight mode using stock PID settings, which are the default PID parameters. When ArduCopter flies with these stock PIDs, its behavior can vary depending on factors like drone size, weight, motor power, and propeller configurations. Let's begin the step-by-step procedure for tuning 10-liter agriculture sprayer drone using CUAV X7 Plus flight controller running with ArduCopter version 4.5.5. Let's start with step 1, motor and battery setting. The motor and battery parameters are important for initial tuning your drone performance. Properly setting these values will optimize your drone flight characteristics and battery efficiency. Battery volt max. This parameter defines the maximum battery voltage. I am using two 6-cell lithium-ion battery pack connected in series. So overall it's a 12-cell battery pack with each cell having maximum voltage of 4.2. So the value I am using for this parameter is 50.4. Next, battery volt minimum. This parameter defines the minimum battery voltage. For my battery pack, each cell minimum voltage is 3.2. So the specific value I have set for this parameter is 38.5. Next, motor PWM max. This parameter defines the maximum PWM output. It determines the upper limit of motor speed. So refer the ESC manual for correct PWM range. So the exact value I have choose for this parameter is 19,950. Motor PWM minimum. This parameter defines the minimum PWM output. It determines the lower limit of motor speed. It is typically to ensure the motor starts spinning reliably. So I have gone with 1040 for this parameter. Next, motor spin arm. This setting controls the minimum throttle required to start the motor when the drone is armed. It ensuring that all motors spin up correctly. In this drone, all motors start spinning at a 10% throttle. So, I am using 0.1 as the value for this parameter. Next, motor spin max. This setting controls the maximum throttle value that can be sent to the motor. For my setup, I am using the default value of 0.95. Motor spin minimum. This setting controls the minimum throttle at which the motor will reliably spin. So I have gone with 0.12 for this parameter. The difference between spin arm and spin minimum is that spin arm controls the motor speed when the drone is armed and the throttle is at 0. But spin minimum is the minimum motor speed once throttle is applied. Next, motor thrust expo. This parameter adjusts the expo curve for throttle response. A higher value makes the throttle less sensitive and the lower value makes the throttle more responsive. For my setup, I am using the default value of 0.65. And next one is motor thrust hover. This parameter defines the throttle level required to maintain a stable hover. For a maiden flight, a starting value of 0.25 is recommended. Now I will conduct a short flight test using only the updated battery and motor settings and keeping all other parameters at their default value. Let's see how this drone fly. The next step is to update the attitude control acceleration setting for this drone. These are maximum acceleration setting for pitch, roll and yaw axis. Proper adjustment of these values allows for smoother and more controlled maneuvers and also helps to avoid issues such as oscillations or sluggish response. ATC axle Pmax is the parameter defines the maximum acceleration in the pitch axis. It controls how quickly the drone can pitch forward and backward. Higher values make the drone more responsive to pitch input. Lower value makes the drone sluggish in pitch movement. The value I am using for this parameter is 38,000. Next, ATC axle Rmax. This parameter defines the maximum acceleration in the roll axis. It determines how quickly the drone can roll left or right. Higher values make the drone more responsive to roll input. Lower values make the drone sluggish in roll movement. The value I am using for this parameter is 38,000. The last one is ATC axle Y max. So this is the parameter defines maximum acceleration in the yaw axis. It controls how quickly the drone can rotate left or right. Higher value makes the drone yaw faster. Lower value make the drone sluggish in yaw movements. The value I am using for this parameter is 14,400. For this flight test, I have adjusted ATC acceleration values for the pitch, roll and yaw axis. Let's see how the drone performs in the air. Step 3 of the tuning process, focus on adjusting the attitude control setting, specifically proportional P gain. This setting is crucial for angle control in pitch, roll and yaw axis of your ArduCopter. These parameters are part of the PID controller. These are most important for fine-tuning the drone responsiveness. ATC angle pitch P is the parameter defines the proportional gain for the pitch angle. It determines how strongly the drone corrects its pitch angle when there is a deviation from desired pitch. A higher value will make the drone correct faster, but too high values can cause oscillation. ATC angle roll P is the parameter defines proportional gain for the roll angle. It determines how aggressively the drone corrects its roll. Similarly, higher value increases responsiveness, but too high value can lead to instability or oscillation. And the last one is ATC angle yaw P. So this is the parameter defines proportional gain for the yaw angle. It determines how strongly the drone corrects its yaw angle when there is a deviation from desired heading. So proper tuning of this P gain is essential for achieving stable and responsive flight, and to ensure that the drone can maintain its intended orientation without overshooting or lagging in response. For this flight test, I have carefully adjusted ATC P gain values for pitch, roll and yaw axis. Now let's check how the drone performs with the updated ATC P gain. Step 4 tuning process, focus on adjusting axle filter and gyro filter setting. The accelerometer helps to calculate the drone attitude and position control. However, accelerometer data can be quite noisy especially in high vibration environment. So, using a low pass filter can effectively reduce this noise. On the other hand, gyroscope measures angular velocity, which is important for maintaining stability and controlling the drone attitude. Gyroscope data is also susceptible to noise, particularly from vibration. The low pass filter works to remove this noise and to ensure the flight controller receive more accurate information. Let's see how the drone performs with the updated filter values. Step 5 tuning process involves adding filters to the PID controller for pitch, roll and yaw axis. These filters are useful for managing noise and enhancing stability by removing unwanted high frequency signals that may create instability and oscillations. There are three filters: FLTD, FLTE and FLTT, each for pitch, roll and yaw axis. FLTD is the derivative filter. It reduces high frequency noise in derivative term and it preventing noise that could lead to instability. FLTE is the error filter. It smooths out rapid changes in the error signal and it preventing the controller from overreacting to small disturbance. FLTT is the target filter. It makes the control response smoother and more predictable. Now let's observe how the flight behavior changes after the updated filter values. Step 6 focus on tuning the PID controller for pitch, roll and yaw axis. These parameters determine how the drone's motor respond to maintain stability and responsiveness. Each axis has three key parameters: proportional, integral and derivative. In general, proportional gain makes the drone respond quickly to error. A higher p-value increase responsiveness but may oscillate if it is too high. Integral gain address long-term error and it helps to eliminate its over time. Derivative gain reduce oscillation, especially during quick movements. I will start the flight test by adjusting pitch and roll rate controller. First, I will increase the gain values by 10% and observe how the drone behaves during flight. Step 7 tuning process is based on the result obtained in step 6. By increasing the gain values 10%, there was no significant difference in the controls. So I have decided to increase further 15% from the default value. If it is more responsive or slight oscillation, then I will conduct another trial by reducing the gain by 10% from their default value. Let's observe the flight behavior. Step 9 is about the tuning of position and stabilization controller in ArduCopter. These settings are crucial for ensuring that your drone maintain its position accurately and stabilize its flight effectively. PSC Axle I is the integral gain for the vertical acceleration. This setting helps to adjust the drone vertical position by integrating vertical acceleration. Next, PSC Axle ZP. This parameter is the proportional gain for the vertical acceleration. It determines how much vertical acceleration will respond in drone vertical position. Next, PSC position XY P is the proportional gain for the horizontal position. It determines how much horizontal position will respond in the drone horizontal position. Next, PSC velocity XYD. So this parameter is the derivative gain for the horizontal velocity control. This setting helps to damp oscillation by responding to the rate of change in horizontal velocity. PSC velocity XYI is the integral gain for the horizontal velocity control. It integrates velocity error to correct steady state error in horizontal movement. Finally, PSC velocity XYP is the proportional gain for the horizontal velocity control. It determines how much the horizontal velocity react in the drone's velocity. These parameters are essential for fine-tuning the drone to maintain its position and stable flight performance. Step 10 involves updating the input shaping parameter for loiter mode. This is important for ensuring stable and reliable hovering of your drone. Loiter accel max. This parameter defines the maximum acceleration allowed when the copter is in loiter mode. It dictates how quickly the drone can accelerate when changing its position. Next, loiter brake acceleration. This parameter is used during braking when the copter needs to reduce its speed in loiter mode. Next, loiter brake delay. This parameter controls the delay before braking start when the copter is in loiter mode. It determines how long the system waits before initiating the braking process. Next, loiter brake jerk. This parameter defines the jerk during braking. It affects how smoothly the drone decelerates when slowing down. Then finally, loiter speed. This parameter specifies the maximum speed of the copter that can travel in loiter mode. These parameters are key to achieving smooth and stable loiter performance and to help the drone hold its position accurately without excessive tilting or sudden movements. Let's see how the drone performs after updating these shaping parameters. Step 11 involves updating the input shaping parameter to ensure that the drone response align with the pilot's control input. Pilot speed down. This parameter controls the maximum vertical downward speed, it defining how fast the drone will descend when pilot commands a downward movement. Next, pilot speed up. This parameter controls the maximum vertical upward speed, it defining how fast the drone will ascend when pilot command upward movement. Next, pilot yaw rate. This parameter controls the maximum yaw rate and how quickly the drone can rotate in response to the pilot's yaw command. These parameters are important to ensure the drone responds predictably and performs in a controlled manner. Fine-tuning these settings can lead to smoother flight and better handling to the pilot preference. Step 12 is the waypoint navigation setting. Waypoint yaw behavior. This parameter controls the drone yaw behavior when navigating between waypoints. It can be configured to various behavior such as maintain the current yaw or pointing nose directly towards the next waypoint and automatically adjust the nose to match the desired heading. Next, waypoint navigation acceleration. This parameter controls the maximum horizontal acceleration during waypoint navigation. It determines how quickly the drone can speed up or slow down from one waypoint to another waypoint. Next, waypoint navigation speed. This parameter determines the maximum horizontal speed of the drone that can travel when moving between waypoints. Next, waypoint speed down. This parameter determines the maximum vertical downward speed during waypoint navigation. Then waypoint speed up. This parameter defines the maximum vertical upward speed during waypoint navigation. So these parameters are important for ensuring your drone navigates accurately and smoothly in order to achieve efficient and reliable waypoint navigation.